可以啊。S 要拜几？拜六、拜二、拜二、拜三。OK，那就很难了。中文拜一要做吗？拜一要做吗？对呀、啊，没有啦，我讲如果拜一交的话会怎样？嗯、为什么呢？为什么啊？我就问你啊。哦，这么拜二就做得出来？也不一定做得出。OK，OK，OK，下周五。嗯，revision week 啊。OK，请请出麦口。OK OK，这样你还要整理那个 final 的 lecture note 吗？还是不用整理啊？OK，这样就算了咯。哦，是哦，OK，let's not wait then。 Today we will try to calculate some very fun stuff, very interesting stuff that maybe you never see or never imagined before. Okay, so we're gonna learn new calculation today. So before that, I want to recall some useful identities, but we are dealing with category now. Identity is not very useful for us mathematician now. So we actually look at isomorphisms. Okay, so what are the important isomorphisms I want to introduce? So if M is a free R module, okay, then X from N to N is 0. I hope you recall this because free module, what's the free resolution for free module? It's just the M itself, right? So X1 is 0 because the C1 is 0, okay, 0 chain group at the C1 position. And there's one thing that I didn't tell you yesterday, right? So if there's a free module map into N, this is actually isomorphic to M, given that, okay, we know that this M is finitely generated. Okay, okay, does it make sense? Because why? Because let me think. So last time we proved that home from R to N is just an R module. Okay, if you still remember this. So what we do was we take F and then we evaluate it at 1 to see where it goes. Okay, so let me recall for you. Let's check is it correct or not. N or M? Let's check. If it's N, then would it be something wrong? Let me check. Where is it? Home. Where's the home? Where's our home again? When we do this thing, I think it's much before this one. It's the green, the purple part. It's N. Okay, so let me think. What's wrong here? Uh, so let me think. So how should I deduce this? Uh, Let me think again. So if I can, that means, is it just N to the how many times of R? Let me think. Let me check. If in that case, it should be just because you have multiple of R, right? So you should have multiple of N in that case. Let me see. Right. I think you were right. You're right. Okay. So I guess instead of M, it is N actually. Sorry, yeah. So this is N to the how many time you have. Maybe this is finally generated. So maybe let's say this is less than infinity. So it's measured by N to the I times. Make sense? That's thank you. Yes. Okay. Yeah. Okay. So it's non-zero in particular. Okay, it's non-zero in particular. Okay. And then on the other hand, we say that one of them is measure freeness, the other is measure the torsion, right? So how about the other part? So the other part we have x from R over AR to N is isomorphic to N over AN. Okay. And last time I proved to you that if you have a torsion group and mapping out, actually you can only have the zero function, right? Because if you compute what is f, apply to the elements inside or t in a over ar. Okay, what is this? This has to be zero because we know that 0 equals to f of a t, and then you can pull the a out because it's a scalar. But then this has to be true for all t, so f have to be 0, since a is not 0. Okay. Okay. So far so good. Okay. The freeness and the torsion. Okay. So we're gonna use this frequently today. Right. So let's start with examples of cellular cohomology. Okay. Let's look at RPN. Well, so let's start with a cellular chain first. Okay, so first step, we start with cellular chain. Okay, if you still remember what the cellular chain is for RPN, it is just Z and then 0 and then Z and then 0 and then Z. Sorry, 2, right? 0, 2, 0, 2 alternating. Depends on you are even or odd, it will stop at either 2 or 0. Okay. Or it will stop somewhere. Okay, and then this somewhere is the n term, Cn term. Okay. So depending on the even or odd, this is 2. So maybe I draw this. So it is 2 if even or odd. You still remember? This one you should remember. Will be an exam. Okay, so calculate lah. Calculate. Even if you cannot remember the degree of Sn, right? The degree of the map. So you can calculate also C0, C1, C2, like that, right? Okay. So you can see that it should be 2 if n is even, right? And then 0 if n is odd. Okay. So then we will dualize this. Okay, we will dualize this to get a cellular, dualizing it to get cellular core chain complex. Okay, core chain complex. So what do you do to dualize it? You just apply hom. Okay, you apply the functor hom of something to z. Okay, so you're dualizing it. So you can anticipate that the direction of the arrow will go backward, right? Go backward, and then similarly, if you check the composition, it will start with 0, 2, and then alternating as well. Okay, alternating. Okay. Go backward. Okay. Then in this case here, what we get here will be, what's the cohomology in this case? It will be Z if K equals 0, very similar to the homology case. Z mod 2 if K is in between n and 0, and K has to be even and 0 otherwise. Okay, so it is there's a 0 in between Z mod 2, and then the first one is Z. This is when n is odd. Okay, if n is odd. Sorry, when n is even. Okay, but when n is odd, what happened here? Okay, when n is odd, what happened? Very similar. Yeah, very similar, except you have an extra z. Okay, you have an extra z because at the last step there, you have an extra z because the map is 0, right? Okay? So the kernel is just Z. There's no image molding it up. Yeah, otherwise. Okay, so there's an extra term at the highest degree. Okay, makes sense. Okay, so let's say we don't want to use Z, we use Z mod 2. What happened? The multiply by 2 maps become a 0 maps. So then we will have Z mod 2 at every degree. Okay, because it's a 0 map. So you have a 0 map on your chain complex, then it is the same homology as your chain group. Okay, now how about let's compare with what we know before. Let's compare with the homology we know before. See if you can notice something special or not. Okay, if we notice, where is the yeah, copy. All right, so okay, look at this homology example here. Can you see what's their difference? Okay, both of them have Z at the 0 degree, huh? And for N odd, you also have Z at the highest degree. But then, did you see where's the appearance of Z mod 2? One of them is in the odd level, right? For homology, is at the odd K. But for cohomology, it's happened at the even K. Ah, very special, huh? Okay, so I urge you to check it out. This is not mistake, not by purpose. It's really what happening here. So for cohomology, your Z mod 2 happen when K is even. But homology, your K is odd. Even 和 odd 会一样。cohomology 是 even 呢，上面是 cohomology，下面是 homology，什么问题？你看那个图，有问题吗？cohomology right in the middle the K have to be even but the bottom one is off. Okay, can you see or not? Actually, this is the symmetry I told you last time. Where hash n hash to uh the n homology is actually isomorphic to the n minus k cohomology. Okay, so this is the symmetry part. Yeah. Yeah. Okay. Yeah. Yeah. Okay. So this is something to do with the point correct duality later. Okay. Where the n homology is equal to the n minus k cohomology. Okay. But if you really see the for the even case, right, there's no duality because there's no two z. There's only one side got z. 0 degree has a z. So the top degree n there's no z. Okay, so actually what it says here is point corollary duality only work for orientables manifold. Okay, so here book says that RP2N is not orientable. Okay, only odd projective space is orientable. Yeah, later we will define it. Just give you an idea first. Okay, later we will try and define it, make precise, really precise what it means by orientability. Okay, using homology. Okay, you have heard these words, I think, starting from calculus already. Orientable, oriented, right? Okay. Or if you don't want to use this dualizing method, right? Actually, there's another way to do it, which is by using the universal coefficient theorem. Okay, because we already learned the homology of it, so you would look at the x term. Okay, so what's the x term from hk rpn to z2, for example? Okay. Yeah, if you look at the z2 case, or if you look at the z case, then you need to do it appropriately. Okay, so you need to figure out what's the x term. And the home term, for example, the home term, you need to take care. Okay, given that we know they are homology. Okay, so there are two ways to do it. Either you use this, or either you dualize it. Okay, calculate from the beginning. Okay, any questions so far? Okay, if you use UCT, then you need these identity to help you. Okay, you need these identity to help you. All right. Okay, then in that case, we will continue. So next part is about Mayer-Vittorius sequence. Okay, so the setup of Mayer-Vittorius sequence is the same. Okay, it's the same, but just that the sequence will go the other way around also. Okay, so again, you want to split your topological space into two interior. Maybe later we'll have just two subset. Two subset with what? Let me see. No, okay, never mind. So this is the form that we also have in homology. So we split X into interior of two open, not really open. It's just two subset. Again, then we will have some long address sequence of homology. So you can see that this is different from the homology case, right? Because in homology case, you have the intersection mapped into the direct sum. And so this one goes the other direction. And the direct sum group into the intersection. Okay. The proof I think is not too hard. Okay, if you understand the homology one. Yeah. Okay. If not, you feel free to skip it. Then we also can have a version for relative homology. Okay, very similar to what we had for our homology case. Okay. And well, one example you can use to compute is compute the cohomology group of Sn. Okay. So we want to cover Sn using two open set here, hemisphere, upper hemisphere, lower hemisphere. Okay. Sn remove the dot pole in the lower hemisphere, southern hemisphere. And then sphere removing the subpole is what is that? What's that? Upper hemisphere. Wow. 你们去 party 啊？哦，大家去 party，去哪 party？哦，OK OK。Nice. Okay. So then if you look at these two intersections, I mean this picture we already see before, right? You have a sphere and then you like cover the sphere from top and bottom. Okay, but what's the intersection? So we need to make it a little bit fatter so that they can intersect. Okay, intersect and then intersect as a circle. Okay, Sn minus smaller circle. Okay, but each piece of them is Rn. Why we love Rn? Do you still remember why we love Rn? Why we love Rn? Why we love circle? This is the only you know how to compute. Okay, so Rn is contractible, so it's just a point. And so we know the cohomology of it. But Sn minus 1 is what we wanted to compute. Okay, so if you still remember from last time, right? It's very similar proof. Okay, we have this induction. It's hi, what? Yeah, hi on that. So the word here, homotopy invariance, is for the Rn part. Okay, so that you can relate the cohomology of Rn to cohomology of point. And then induction, where's the induction for? Yeah, induction is coming from the long exact sequence you compute. Okay, because the long exact sequence of Mayer-Vittorius deal with what? Deal with the hemisphere A and B and the intersection of hemisphere. Because if you split out this term, what happens? What happens to this direct sum? both 0 in almost everywhere. Remember, because both of them are Rn. Correct? Yeah. This term is always 0 except at one point. And then this term is reducing the xn to xn minus 1 because you look at the intersection of the two carbon. Okay, makes sense. No question? Any question? Very similar calculation. Okay, just that you move your error the other way. Cohomology. Okay. Yeah. I mean, so far what we know, we know about cohomology of a point is the same as a homology of a point. Yeah, and then cohomology of a sphere also the same as the homology of a sphere. Yeah, last time we compared. So these are the two things maybe you want to remember. Let me see it. Hey, Rachel, just now I saw you smoking the other direction. Buy stuff? Oh, okay. Interesting. Okay. Good. Okay, so we come to a very interesting part of this course. Cup product. Yeah, cup product. Why is a cup product? Because we're gonna draw this product like a cup. Right? If we got chance later, we can go to a cat product. Cat, 帽子. Or cap is like this. So one is cup, one is cap. So this is the two things you want to learn if you are algebraics. Right? So one is cup, one is cap. Maybe you want to think of concave outward, concave downward. But one we will call cup, the other we call cap. Okay, so we'll learn cup first. Huh? Intersection and union. Oh, that one is too cheap. Huh? No, it's different. It's different. It's different. In latex, it's different, I think. It's different. Union is like this. Is it? I think different. Same or different? Huh? I feel like different because cup and intersection and union is how to say. So this is like x to the 4. This is like x squared. Is it? I feel like it. I think they got difference. Got different. 是咩？哦，看的 cat 咩？cat 好像不是，是咩？Is it seriously？我记得比较肥一点的哦，没有比较肥一点的，不懂。Big cup 应该是长一点，把 range 拉长一点，range 跟 domain 拉长一点。哎，我记得 cup 是比较 shallow 的哦，如果我没有记错，对，maybe。但是我看，应该还有别的 notation。我记得这个 union 会长一点点，然后 cup 是短短这样吧。好像那个你有看过吗？那个犹太人戴的帽子。哦，犹太人戴的帽子盖不完你的头。对。好。Okay, but anyways, okay, good. So this we will learn cup product first. So why do we learn cup product? For example, this one now we talk about homotopy equivalence. So CP2 and X2 with S4, right, they have the same amount of cell. Okay. If you still remember CPN, right, they have even dimension cell. So 0, 2, 4, 6, 8. Okay. So obviously there's no boundary map that they are differ by 1 degree already. And then that degree is a 0 in between. So there's no boundary map on S2, where's S4? S2, what's the CW complex we can build? The easiest one. We just take a 2 cell and then cover a 1 cell. So you just need 0 cell. So you just need a 2 cell and a 0 cell. S4 also the same. So all the Sn is the same. You take an n cell, cover, map the boundary to 0 cell. Okay, so S2 with S4, what are the cells? 0 cell, 2 cell, 4 cell, same number of cells. And then they In between the odd degree, there's no non-zero chain group, so it have to be zero map. So the chain map is the same. So does it mean that they are the same space or not? Or homotopy equivalent space or not? Okay, later we'll see that it's not. Their homology is the same. Cohomology, I think, also the same. Huh? Yeah, earlier I forgot when. Oh, yeah, definitely. So their pi one is what? Do you know? How's their pi one? What are their pi one? What's their pi one? You should use the cell structure to determine. Do you still remember we relate the pi one to cell structure? Trivial because here got two cells. Yeah, here got two cells. So the loops can be contractible. All the loops are contractible. They are two cells. Remember? Yeah, remember there's a proposition on pi one that relates to cell structure. You attach two cells. If you have more, you have two cells and above, then you are basically contractible. Your loops can move inside the two cell. And there's a homotopy. Yeah. Okay, so we're gonna show that this is not homotopy equivalence. Okay, because they are cut product. Now we call it cut product. Are different. So meaning cut product can detect homotopy. Smile, huh? See? Okay. Oh, and the wheel package. Slip smile. Kevin. 你看我就讲这个 union 找不一样。哎，你要不要 send 给我？send 给我这个图，send 给我这个图，send 给我这个图，等一下，你打好 send 给我这个图。OK，so yeah，看一下有没有比较那种的 cat，不一样啊，不 symmetry 啊。哦，OK，对，找到 cat 嘛？OK，so then we will define cut product now. Okay, so this is a very historic moment. Cut product. Okay, so so let phi be a co-chain element, okay? And psi as another co-chain element. So we will take the cut product. So cut product meaning take phi cut with psi. We get something in where? What do you think? Where's this co-chain element should live in? What do you think? Which level? You okay with this notation? These are just coefficient. So what level do you think it should be in? K plus L. Okay, K plus L. So why is it K plus L? So meaning what? So what does this co-chain means? Maybe need to remind you a bit. So this is actually a singular homology. Okay, so singular homology. So we will add this cut product on a on a 等一下，对，但是还是要 brown。Okay. But it will add on this singular simplex here. Is it correct or not? Yeah, correct. Okay. So what's this co-chain element here? This co-chain element here is a home from X to R, right? Okay. So you start with a singular simplex. Okay. You start with a delta complex, delta simplex from K plus L to X, and then this co-chain element will help you send to R, evaluate. Remember, cohomology is about evaluating because it's a home from the topological space to a ring. Evaluate. And evaluate. Okay, so how to evaluate? What do you think? Phi can only process K of them. psi can only process L of them. You got K plus L of them. What can you do? What can you do? Huh? Split. Good, very good. Just take the standard split. So you split from V0 to VK first, and then you let the rest get acted by this side here. Yeah, you split it. Very good. Okay, I think this is only by convention, I guess. Maybe you can split in different ways. Right? VK plus 1, huh? Okay, I think no, it's VK. Count. Is it? I think it's VK. Here also you start V0. Yeah, you try and count, see correct or not. I think it's VK. Okay. Then so this is just defined on core chain level, right? So we want it to work on cohomology level. Okay, so we want to show that it is well defined there. Okay, a bit like how we show the induced map is well defined on homology. Do you remember the quiz that we did last time? Well defined. What do you need to check? Check map, right? 怎么还有笑脸来哦？太厉害了你。OK，学一下这个。OK，yeah, so we need to show that it will sense boundary to boundary and then sense what to what? Kernel to kernel, right? Okay, so these are the things we need to check. Okay, or let me give you the statement. Cut product of two co-cycle is a co-cycle, and if either one of them is co-boundary, then the cut product is also co-boundary. Okay, so you will show the well-definedness. So remember last time, the chain map will help you send cycle to cycle, right? And then boundary to boundary. This is similar thing we want to do here. But this rely on only one identity, okay? Only one identity we need to know here. So this identity is very powerful. So this identity is, if you add the boundary map on phi cap psi, what you do is Leibniz rule. Okay, Leibniz rule. Delta phi cap with psi plus, but a bit different here. There's a alternating sign on phi cap delta. Okay, Leibniz rule. Products rule, for example. Okay, but kind of like graded version. Okay, meaning there's a differ of sign here. Are you interested in this proof? Sorry? Graded version of product rule. Okay, later I'll make that precise. Later I'll make that precise. Yeah. Okay. Graded. Now inverted first. Later I'll tell you what's graded mean. But it's like product rule, right? So you differentiate one side plus differentiate the other side. Boundary map. Did I use delta here for here? I use delta or I use d to the something n like that. I forgot already. Okay, good. Okay, good. Okay, you interested in this proof? If not, I written in the notes. You can have a look. Basically, you are interested in the sign, is it? Okay, so how to prove this? Basically, you just write out what is left hand side, what is the right hand side, the two terms, and then you see that they cancel out, only left with the middle term, the right hand side term. Okay, so they cancel out. So the alternating -1 to the k, you need it to cancel out some unnecessary term. Okay, this is the idea. Okay, so from here, can you see that? From here, can you see that the cut product of two core cycles is again a core cycle? Can you prove this directly? Okay, meaning you need to show that delta of 5 cap psi is 0. Can you see it from this Lemma here. Co-cycle means what? You are the kernel to the boundary. Okay, so delta 0 is delta phi is 0. And then delta psi is also 0. So the whole thing is 0. So the cup product is the kernel, is living inside the kernel of the boundary. Okay? Make sense? Okay. So another thing is if either one of them is co-cycle or the other is co-boundary, then everything is a co-boundary. Does this make sense? Co-boundary meaning you can write it as an image of a boundary map. Okay, so one of them is co-cycle, one of them is co-boundary. Okay, meaning what? Co-cycle one will disappear. Co-cycle one will disappear. Then you're just left with this term here. Okay, let's see. So let me write something. Another corollary. Let's say if without law of generality lah. Okay. I'm not sure if I write this is the right way to write. Okay, don't want to. Yeah. I don't think so. Yeah, don't think so. Huh? What do you mean? No. It's not commute, but the fact is still the same. So if either one, yeah. I mean, the calculation is similar. Okay, so if either one of these is co-cycle and the other is co-boundary, then we will claim that the cup product is a co-boundary. Okay, so let's try and see this. So let's say proof. Say delta phi is 0, and then psi is delta eta, so meaning it's a co-boundary image of the boundary map. Then we want to study what is phi cap psi, okay, which is equals to phi cap delta n. Okay, sorry, 什么 smile. Okay, yeah, smile. Okay, and then we can complete it to this formula here, right? We can complete to this formula. How do we complete it? Well, are you guys okay that if I multiply minus 1k across like that? Okay, so instead of putting minus 1k on this term, I can put minus 1k on the other term, right? So plus minus 1k on delta phi union, small theta. Okay or not? Okay, then we'll get minus 1 to the k of delta of phi small theta, like that. Okay, using the formula. Leibniz rule. Leibniz rule. Okay, graded Leibniz rule. Okay, because this term is 0, right? So it's nothing this one. Because delta phi. Maybe one thing you want to prove is 0 cap everything is 0. Is it easy to see or not? 0 cap everything is 0. 0 is 0 map, correct or not? So if you evaluate, this term will become a 0 map. So 0, I mean 0 times everything is 0. So meaning what? This cup product actually boils down to the structure of your ring. Okay? If your ring is associative, this guy should be associative. If your ring is distributive, this is distributive. If your ring is commutative, then this thing is commutative. Oh, this is not commutative. Okay, but associativity and the distributive will hold at least. Okay. So corollary is we have a well-defined map on the cup product on cohomology. So far, any question? Okay, we'll define product. And maybe you can ask a question, why can't we do on homology? 什么意思？啊，你讲这个箭头要反的啊？哦，这个箭头把高的抬出，这样才肯定会咩？你在 if you are kernel at the higher boundary, right, then it's, you can split into kernel of the lower boundary. Always possible. Or is there even an example that's possible? Yeah. Can try and think about it. No, no answer. No answer. No answer. Can write as a project problem. Yeah. I think quite interesting. We can discuss this. Okay. Right. So what's next? 245. Okay. So another thing is in this case, right, we have distributivity, associativity, right? Actually, if your ring has an identity, you also have identity here. And the identity will appears in the 0 level, okay, where you take value 1 at each singular simplex. But what happens here is this cut product, right, will help you form a ring structure actually. Yeah, a ring structure. So how do you view this ring structure here? You just not only look at every level here, okay, not every level. Instead, you take the direct sum of all levels. Okay, direct sum of all levels. So your ring is like all the core homology level direct sum. Doesn't make sense. Doesn't make sense. Direct sum just saying that every element should live in the right space. Yes. 加 I think is just sum. Just a formal sum. Okay, that's good. Yeah. So actually, the direct sum is to its addition close. Addition close. Yeah. Product. Because your product will go to different level, right? Yeah. So you need to do the direct sum. All the level together. Does it make sense? So let's say this is H1, right? This is H1, right? You go to H2. Okay. So if your ring is just H1, then your product will go up from H1. So you need to add up all your homology level together. So it's a graded. Yeah, later we'll say why is it graded. So basically this graded means you have different level. Okay. So the level of K, level of L, cut together, you go to the level K. Okay. Graded means there's a level here. But later we'll define it properly. And for now, I just want to tell you that there's some ring structure here by taking the direct sum of all level of. Okay. So far so good. Okay, we will define what's graded ring structure later. Okay. Shall we do one example before we take a break? Walao eh. Just now delay my time now. Okay, let me finish one. Okay. 我只是好意思问你吧，我要继续。喂，现在才48分呢，正常上课还要至少到50分呢。Okay, let me finish one example. Okay. In fact, let me see. Okay, I will discuss 3 examples on the same space. Okay or not? Buy one, free two. Okay. On the same space, we're gonna see the cohomology in a different way. Same thing in different way. Okay, so first two way is using different CW structure, or delta complex structure. And then the last way we will see is uh, singular cohomology. Okay, yeah. So one is to use function to see, the other is use delta complex to see. Okay, make sense? All right. Let me check first. Okay, let's do it one by one. Let's do one and then we take a break and then we do the other two after the break. Okay. Okay, so this is a very cool calculation. All right, so we will see cohomology of RP2 in three ways. Or I mean cut product lah. Cut product in cohomology. Three ways. Okay. So let's do the first way first. Let's do the first way. So just now we discussed that, recall that we know the cohomology already, right? For RP, we even know until RPN. Okay, so now we just look at RP2 first. But the Z mod 2Z condition. So what is good about Z mod 2Z in our projective plane condition here? Okay, why is it good here? Because the boundary mat is multiplied by 2. So if you mod 2, the boundary mat will become 0. Okay, then it would just be the chain group itself. Okay, for 0, 1, 2 level, because your RP is up to 2, right? So it's non-zero in this 3 level here, and then it's 0 otherwise. Okay. So your cohomology are only non-zero in this 3 level, H0, H1, H2. Beyond that is nothing. Right? So just now, if you think about cut product, right? If I take two elements from not two elements, Z mod 2Z means what? Every level there's only one generator. Correct? Only one generator. So if you take the 0 level times the 0 level, what you get? You get the 0 level again. So not very useful. But if you take the first level times the first level, just now cut product says what? Become the second level. But your second level only got one thing. So we want to prove that actually the cut product of the first level is actually the generator of the second level. Okay, this is what we want to show. Okay, yeah. So this is, we want to show that we can get the generator of the second level from the cut product of first level. Okay, so this is what we're gonna do. So let alpha be the generator inside the first level. Okay, first cohomology here, because first cohomology is generated by one element only. Okay, isomorphic. So let it be the generator. And then we will look at alpha square, okay, which is in the second level. And then we want to show that this alpha square here is non-zero. Then if it is non-zero, then it is the generator. Yeah, right, correct or not? Okay, because Z mod 2Z is invertible. And so if this is non-zero, then we will prove that the second level of second cohomology here is generated by alpha square. Okay, so how do you understand this alpha then? Right, if we want to talk about is this simplicial here? Yeah, simplicial cohomology. Okay, if we talk about simplicial cohomology here, then we need to define our simplicial complex. Okay, so let's draw RP2. So still remember how to draw RP2? What is RP2? Right? Okay, then attach one cell and then attach the cell. But the problem here is how to attach. The attachment is different. You attach different way, you get different space. Okay, so the way to attach here is you have a two cell that join to this one skeleton by identify these two lines here. Let's remember identity map and then antipolar map. Okay, but this is not quite a delta structure yet, right? We want to make it a delta structure. So 什么？给它一个名字吧。这两个是同一条线，我要 identify 它们。Yeah, yeah. So go different direction, right? Because antipolar map. Remember? Huh? Remember the RP2? Okay. RP2 got a two cell, right? So we will attach two cell along this one skeleton. 这个是 RP1， right？ 这是 RP1。它的 boundary 啊，RP2 的 boundary 是 RP1， 是吗？是这样讲啊？Yeah, yeah. 没有环的跟那个一是一样的东西，because they are homotopy equivalent 嘛。Correct or not? Okay 啦，I put a hole for you. 啊？好。Yeah. But anyway, they should intersect at one point. Okay. Okay, and then so we want to have a delta structure. So meaning we want to split the two cell into maybe at least two delta. So we can do like this. We can add another vertex in. Let's add another vertex. And we can add another edges. Let's call it this E1 and then this thing called E2 maybe. 直的就很难分辨他们两个。原来你在意这种细节。Anyway, so we add a new vertex here, V, but top and bottom we identify, right? So there should be the same vertex. So let's call it the view. Okay. Yeah. So the addition of this vertex and this two line is just to do triangulation, just do the delta. 是吗？是三角形吗？是三角形。是哈，因为有三个角嘛。对啊，也有三条边。只是 yeah. But anyway, this is topology. Yeah? Okay. So and then your two cell will split into let's say T1 and T2. So far so good. 问题吗 ？Yes. 那不是他问了没？我回答他了，你回答他一下。啊，我画一次给你看了，画一次给你看。那这样。我觉得让你觉得就是一条线是个大画的歪歪。因为你们大家都在意这种小细节，好吧？太棒了，来 ，OK， 对，没有啦，我是怕这个过后感觉好像太齐了，太齐，对吧？对，哎，但是这个不是我画，我是看到那本书画的，Yeah，but anyway， 那阿摩人画，cover page， 哦，cool， cover page， 是。OK， 我觉得可以放两只鱼进去，放两只那个锦鲤进去。OK，Anyway，right， so right， so let's continue. Should we continue? 还是停在这边先呢？还是你们有问题吗？没问题。Okay, so remember our goal. Later we will do it. So okay, we can break now. Let's break until 3:08. 哎，今晚那个 library 有表演哦，如果你们有在，可以来看。我不在。哎呀，可以叫你们朋友来看。今晚9:30，在 library。我会去 study group 已经。没有，我 advice 哦，Yeah，assignment， 你们要 extend 到几时？没有 core module 的东西啊。那，我成熟了，我还没。不然现在看，给10分钟看。半夜才懂。喂。 我靠，
surprise 我看见
什么怎么办？我放很久了，好不好？小叶，assignment 看了吗？还没看。谁看了 assignment 到底？
我会做2题。
哦，会做2题。我就觉得要多长时间？
我做了几题啊？
哦，啊，你交了？怎么每次是这样快？我靠 ！Good, good, good, good. How long you spend? Few days. 什么叫 hours? Few hours. 那现在没现在。
没做2
天。对，你很厉害耶，你们其实这个 assignment 我要做1个星期了。你们给我做2天就可以了，太强了。
13个比赛应该没有多
3分3号就行，
要快一点。
花了4、5个小时。
下个星期一
可以。
下星期一，可是你们还有 report 几时要讲？
再想。
他讲 exam week，不 study week 星期一，study week 星期一还是什么？没有，这个不是，这个是 project， 那个 assignment 是下个星期一。哦，可以吗？好，
我今年。
真说啊，
下个月3个月再可以。
啊，对吗？合理吗 ？OK 啊 ，OK。
你的另外一个 format 可以帮你干什么？
对，
你的另外一个 format 干什么？
哪一个我？
找你们。
你好屁股。
不懂哦。
对啊。
他上个礼拜有去 presentation 那个谁讲？
那没
中医的 presentation。
那我做啊。
他们拿 G。我叫驼铃去找他也都不。
啊？
上个拜五有看到他。
对啊，莫名其妙一出新闻的20多人。
你们怎么当他们
苏珊，
发生在他小
什么道具啊？
发生他小的恋情。
知道。
哦，打的是今晚没？哦，看一下涨价了。
多少钱哦？
涨安装，有钱啊？什么钱？不是这个要钱我知道，但是上面写什么？那是支票啊。
反过来看啊。
支票。算不出是不用拿这个钱了是吧？
有一个 bug， 这个怎么办呢？是 condition。
哦。
什么？虽然说他给你任何钱，所以你可以有可以。我不给建议。
OK，是。哎，现在我想问一下 P 那是意思什么？什么叫 P？
Fiber 嘛。
然后 Fiber 又怎样？
一个 Fiber。
我知道，是。
你是 Metal。
球，这样都会不要叫 Fiber， 我感觉更好。好 ，OK。
飞就是啥意思吗？
他讲的是 fiber， 因为 fiber 就是一整条皮面嘛，那 projection 皮面，很多层的，下一个层
就是层的一组人。
我 present 了，不是我是什么？
你要 present 啥 ？Korean。哦，你看下个星期。好，这个是。
哎，你被上视频看了？
怎么？
早上超市花在8小时开始要收，
发什么？
巧克力。
哦，chocolate。
当时说这明显不可以吃的。
是经济有问题吧？现在。
对啊，经济很问题，超级红诶，很恐怖。
别问股票，你有很多的股票不对。
哎，可是我看了明年的我运势嘛，
乱叫。
明年可以赚到。搞笑。没有，我没有赌我的投资。
别人开会会讲
啊，
好吃笑吗？
什么开会什么？
开会会讲
哦，我不是玩那种，那种有一点像那种赌比赛这样那种，开盘哦，有啊有那种，我不知道现在已经玩，
你是
像比赛一样，
就是说
有，
你
啊，
呢？
好像我们谁做首相也会有赌盘的吗？我票前一晚啊，怎么？
用 Delta Complex 做的叫做 Simulation。
嗯哼，
用 Simulation Complex 做的是什么？
什么意思哦？Simplifier complex 跟 simplifier 什么关系？什么差？
知道没？
哪一个？Simplifier complex 啊？还是 simplifier homology？还是 simplifier cohomology？哪一个？三个都是在用 simplifier complex 做出来的。两个都是用 simplifier complex 做出来的。
是 Delta Complex 做出来的。
你给我想一下，什么叫做 simplifier 了啊？
然后我们过后还有
singular 是 singular 是看那个 simplex 那个 simplex 怎么 map 进那个 那个 Topology 里面，yeah 然后
因为他做
这个是 singular，
看不上，
然后 simplifier 就是 delta 了simplifier 就是 simplifier complex 就是 delta 了吧？
不一样的，
这样
你现在好像更加简单。
没有啊，要 complex 先啊，delta complex 先啊，simplifier start with delta complex。
对啊，所以你要标自己是，但是还有一个 complex 叫做 Simulation Complex。
哦，那个我看一下，
我也很怀疑是这么 Simulation Complex，但我没有理解，
其实有个他是
我没有理解过。那我很好奇是为什么他们一定要换那个名？叫到 complex 就做
OK，可能你的 simplifier complex 是不是这个东西？是不是这个？你去哪里看到那个字？我没有介绍是吗？是这个东西是吗？是这个吗？是这个 XX 吗？这个东西你叫 simplifier complex 吗？他说 simplifier complex，
就不要，
是吧
可是 simulation homology 不就是这样？
？Simulation Complex 是它还要求一个 section 只有一个点，
哪里？看一下。
但是有时候我非常恐惧，因为 homology 叫 Simulation Homology，但是它 complex 要怎么
这个好像有一点点不一样，这个好像去除了很多 extra 的东西。
它好像比较简单。
对，我觉得如果没有错的话，可能是这一个，maybe SX 这个东西，应该是这个。不过，可以探讨那个，但是不是我们讲的呢？OK， anyway, so let's continue. So let's continue this. So we know that alpha will generate H1 P2, but at the same time we know that this is isomorphic to the home from H1 of RP2 to Z mod 2Z because you can use the extension to calculate. The extension is 0, okay, because it's free for H0. Okay, so then we can represent it as a function from in particular from C1 of RP2 to Z mod 2. Well, so what's this function here? So if you learn ALA, this is a kind of a dual isomorphism here. Yeah, if you learn LLA here, this is exactly the vector space and the dual of the vectors, dual of some other vector space. This vector space, H1. H1 is a vector module, correct or not? Yeah. So this is represented by a map. So this map, okay, so what's this map? Let's describe this map. So this map will map from C1, the level 1, to Z mod 2Z. Okay, we pick a representative, that's why we map from C1. And then this phi here will satisfy phi E equals to 1. Okay, does it make sense? Because E is the non-zero one simplex here. Okay, you want to evaluate that to 1. If you evaluate that to 0, then nothing you evaluate to 1 already is a 0 map. Okay, so this is the obvious non-zero term here, and then through this isomorphism, actually this is the correspondent. 啊？
还是里面的东西？
还是里面的东西啊？还是
泛义会对，泛义会对。
我要告诉你它怎么define 嘛，这个 map
哦，所以你的意思是
会把一送去一。
因为右边的东西会把人变成
Yeah. So I need to tell you what this map is.
actually there.
Huh? Yeah. Okay. Anyway, so because at the same time we know that the generator here is generated by. Okay. Anyway, so let's continue. All right. Huh? Can we not be? Yeah, I think. Yeah. You can regard it as E now. If you change basis, nothing basis for you to change, right? There's no basis for you to change, right? There's really two things only. You cannot change to other basis anymore. Yeah. Again, in this case, it's easy. Okay. All right. So then there's a core cycle condition. Okay, core cycle condition here. What do I mean by that? What do I mean by that? Okay, so what do I mean by that? I forgot why. So why do I want to let this phi to be 0? Let me think about it. So if you map your boundary map on this H1 here, oh, obvious. Okay, so because H1 is the kernel, right? And then everything in the kernel you map by the boundary map, what do you get? 0 again. Okay, you already is 0 in the previous boundary map. Then you apply delta again, you get. Oh, wait, sorry. This is the definition of H1. Okay, the definition of H1 is what? You apply delta, you get 0. Kernel. H1 is kernel mod out by image. Okay, yeah. So the thing inside kernel is evaluate to 0. Okay, so this thing will evaluate to 0. Okay, let's check the map on T1. Okay, but on T1, what do you get? So I mean on this phase, first phase here. So this is 5 on delta T1. Still remember how the core boundary maps act. Okay, how the core boundary map act is by acting on the boundary of your cell. Okay, so what's the boundary of your cell? Okay, so you look at the boundary law, this one, and this one, right? Okay, so actually it's, if you believe me, it's phi E1 plus phi E minus phi E2. Okay, so meaning you need to put orientation on your delta simplex, right? Orientation. You know how to put orientation? Is it the right orientation? Go up and then go down and then go down. So meaning this W has the highest order. Okay. And then on the other cell, two cell, what do you get? Okay, you also add on the boundary, you get phi of E2 plus phi E minus 5 of E. Okay, so this is the core cycle condition we mentioned last time, because you want to you want this to be 0, but at the same time you have some image on your boundary, and then you want to make sure this sum is 0. So still remember last time I talked about the core cycle condition in the arithmetic, when you add like 7 plus 6, y is 13. So what's the carry over function doing there? Okay, to satisfy some associativity core cycle condition. So this is similar, okay, core cycle condition, because you want to make sure it is living inside the cipher, call cipher. Okay, yeah. Because phi, okay, so since del phi is 0 as phi is in the hash. Okay. It's a zero map. Okay. Yeah. But then at the same time, it is a non-trivial definition. Again, you need to apply phi on the boundary. So you need to measure the left-hand side and right-hand side is equal. Okay. So then we know that how we evaluate phi on E, right? So this one term is 1. So this term is 1. And then this term is 1. Right? This is the two term we know. So how to make this sum to be 0? What do you think? You got phi E1 minus phi E2, right? And then you got a 1. Okay. So what can you do? Actually, minus sign doesn't matter here, right? Because we are living in a Z mod 2 space. Okay. So then if you want to add up to 0, how? The parity must be even. So you have to send either E1 to 1, E2 to 0, or E1 to 0, E2 to 1. Okay, one of it is non-zero. The other must be 0. Otherwise, 1 plus 1 plus 1 is 1. 1 equals 0 contradiction. Okay, so without loss of generality, okay, actually define phi of E1 to be 1, and then phi of E2 to be 0. Then next, because phi is represented by the phi we had, right? Then alpha square is also represented by phi cat phi. So let's see what is phi cat phi. So we want to show that phi cat phi is non-zero. Okay. Is it non-zero or not? Okay. What do you think? Is it non-zero in one of the phases? Okay, because phi cat phi is living in the second level, right? Second level is acting on the 2 cell. Okay, so you need to check it on T1 and T2. Is it 0 or not? Okay, so what is T1 and T2? Like just now what Jingsen said, right? You need to split up your 2 cell into 2 1 cell. Okay, so you have to split the T1 up. So what is the 2 1 cell? You must split it up. So one is E1, one is E2, one is E. Okay, 0 to 1, and then 1 to 2. Okay, 0 to 1, 1 to 2. So 0 to 1 is E1, and then 1 to 2 is E. Okay, so what's this number here? So we define this number is 1, and then we define this number is 1 as well. So we get 1. 1 times 1 equals 1. Okay, happy? Happy? Okay, if you check it on E2, T2, actually you will get 0. Okay, because we define phi E2 to be 0. So 0 times 1 is 0. Okay, so what does it mean here? Because okay, so this is like represent the equivalent class problem, right? So we want to compute something on alpha, but alpha is a homology class. So we want to pick a representative to compute. Right? Yeah. Shall we continue? Continue. Okay. So this is non-zero. I proved to you already because it's non-zero on one of the cell. Okay. Any questions so far? Questions so far? Any question? It's non-zero on one of the 2 cells. So it's non-zero. 竞争解释一下。再问一次。用这张图我给你图，帮我解释一下。什么 ？Generator 都是一。 没有，他问你怎么这一个算成这一个啊？刚才你不是讲了 couple 的 definition 吗？解释啊，来用这个图，不是讲 split 咩？对不对？You split the T1 嘛，split into two one cell 嘛。So which is the two one cell you pick? 0 to 1 and 1 to 2. So 0 to 1 is here, 1 to 2 is here. 对吗？这个是我的 order 嘛。哎，我画给你看。So here is 0, here is 1, here is 2. 看一下箭头对吗 ？Orientation order 对吗？是不是全部去最大的下面？Okay, 0 to 1, 1 to 2. 另外一个就是2 to 1。I mean, yeah. Okay. If you notice, very special here, huh? We kind of like neglect one of the simplex in the two cell the two simplex, and we neglect it. I think they done it on purpose, and seems like it's enough just to look at this. Okay, because these two actually cover all the points already, right? Cover all the points. All right. So it's non-zero. Okay. Okay, happy for this one? Okay. All right. So let's look at another triangulation. Should we do this? Maybe we do the next one. I think not enough time. Should we do it? Let me think. Okay, maybe we don't do that. I scared not enough time later. But I want you to see from this example here. Let's say I cut again. I cut 5 to 5 cut 5, meaning 5 cube, alpha cube. What do you get? 0. Why? Because H0 is nothing. We only has non-zero group at 0, 1, 2 only. So this will force alpha cube to 0. So that means there's a relation there. Alpha cube is 0. This ring is generated by alpha, but alpha cube to 0. Alpha square to something non-zero, but alpha cube to 0 because there's nothing already. Third level, nothing. Okay. So this is a relation you put on your ring. 什么 ？OK 吗？听得懂吗？听得懂吗 ？OK. So yeah. Okay. Okay, so later you will see, I'm not sure later or not, maybe later. So later you will see we can write H star of RP2. H star here meaning I take all the direct sums because I cannot list down all the degree. So I just put a star. It's like how you write the chain complex. And then this is isomorphic to Z2. Adjoint alpha and then over the ideal generated by alpha cube. Okay, so you see this is like a bit like the flow of abstract algebra. First you see group and then now you see ring. But now the level is you have topology on them. You have spaces on these things. Okay, yeah. Is it fun? Okay, instead of just see rings, see groups, you see a topology. 啊？喂，我跟你讲了有点困，所以有没有谁在听？没有一个人在听。Oh shit! So hairstyle is like we don't specify all the degree. Okay, we just regard it as the direct sum of all the degree. 哦，对对对对对对，有点像那个我们写那个 chain complex，不是也是这个情况吗？我们写 bullet，或者翻 bullet 就比较好嘛，因为不会。
我们看的也是一个。
OK，好吧，随便都可以。我们只是要一个符号吧。OK， I'll show you the next. Okay, next we'll use singular homology, singular cohomology to talk about it. Let's see. Okay, let's start. So let F be a singular one core cycle now. Okay, just now was a simplicial one core cycle. Now let's take singular one core cycle. So represent again the alpha group. Okay, the alpha element in H1. Okay, this is what we had just now, right? And then what does this F do actually? Okay, what does this F do? Okay, we at the same time we use the same logic just now. This is isomorphic to H hom from H1 of RP2 to Z again. Then again is the E the E appearing just now that define this F here. Okay, so at this level here, maybe I will draw this picture. So in this case, can we change it to lambda so that I can keep to my notation? I scan later, I change E, change lambda, change E, change lambda, then you confuse. I also confuse. Okay, so this singular map you need to talk about is how I map this simplex into my space, right? So how do I map into my space? Let's draw it for you. So we will map lambda to lambda, and then the constant one, meaning we squish it to a point here. And then there's a point upstairs as well. Then these 2 points identify again. Okay, can make sense or not? You got a triangle, okay? And then you identify these 2 sides, and then you set this whole line group. Okay, and then you identify these. And this constant point here and this point is the same. So that you can get the picture. Okay, so this is a singular simplex, because this is a delta simplex. So maybe I write here delta 2 to your RP2. Okay. Good. All right, let's continue. Before that, so we need to note that this F send lambda to similar to what we had send E to 1. Now we will introduce something called a constant simplex. So let's constant 1 to be the constant 1 simplex. So meaning you send the 1 simplex to a constant pointer. And then we also introduce constant 2, meaning you send the entire 2 simplex to just a point. Is base point important here? Why do we say base point here? Let's forget about it first. Okay, so let's compute what is f on constant 1. Okay, so f of constant 1, you can regard it as a f of the boundary of constant 2. Okay, but then what is this? This is just the core boundary f constant 2. Okay, but this is 0 because this is by the definition of H1. Okay, this is how we pick f. Okay, so this calculation we will use it later. Maybe something you want to work out is maybe it's this part. Why partial of constant 2 is constant 1? Is it obvious? Okay, maybe you can think about this. So constant 1 send 1 simplex to constant, right? And delta of constant 2 means what? I think you should look at the boundary of the constant 2 simplex, right? But your map is sending everything to constant. So you're going to send the 1 simplex to constant x1. Right? Then consider sigma. Okay, so consider this guy here. Okay, this guy, call it sigma. Sigma. Okay, what's this sigma here? So let's look at F cap F on this sigma. Okay. F cap F on this sigma here. So we want to, yeah, sigma here. Okay, this sigma. Okay or not, everyone? This sigma here. Okay, we look at the caps on this sigma because we want to look at how it act on the singular simplex. Previously was just simplicial. Now you need to look at how it act on this function here. There's a lot of function going on. Please don't confuse it. Again, what's the definition here? You restrict your sigma to the first two vertexes, and then times f restrict to the last two vertexes, split it up. Okay, same idea. But then what is these two? So these two is like so this orientation become very important now. 是啊咯，就做错了。Let me think. So I want this to be f lambda and f lambda. So let's check. 错了 ，good， 非常好，错了。So I guess 这边要放0。Wait, how it works? Wait, let me see. 其实是 OK 的，因为 yeah, okay, actually, okay. This is fine. Okay. So actually, we want 0, 1 to be lambda, and then 1 to 2 to be lambda as well. So doesn't matter, right? Doesn't matter, right? Because we use this as our two simplex, and then we do the appropriate gluing. Is this gluing okay or not? Yeah, 我放错东西了。So if here is going downwards, right? Here should be going upwards. Yeah, okay. In that case, this is correct. I draw the wrong picture in my notes. Okay. Because if this side is going down, that side should be going up. Okay, so we're following this two simplex direction. Okay. Okay. Yeah. Can follow? 有问题吗? If I go down on the left side, you should be going out on the right side. Yeah. Then this will follow this simplex orientation, 0 to 1 and then 1 to 2. And so you split at lambda. Good. So then in this case, this is 1. Okay. So meaning what? Meaning this cut product takes value 1 on this singular simplex here. Just now we are taking value 1 at the T1, right? 1 of the T1, one side of it. But then if you check it on constant map, right, it is 0. Okay. Yeah. So just a sanity check. If you add it on constant, this is 0. Later we'll use this. What do I say? Use this calculation. Okay. Because constant on two simplex, you send everything to constant. So when you split to their boundary, also go to because everything go to constant. Constant here is 0. Constant here means 0. Oh no, it doesn't mean 0, but this is from what we proved that it is 0. Okay, f of constant is 0. Okay. Right. So then we claim that so the next claim is f cap f is not a co-boundary. Okay, otherwise it will become 0 in our space. Okay, so suppose otherwise. Okay, suppose it is a boundary. Okay, so what happens here? Then we can compute from this computation that we did on sigma. Okay, and then if it is a boundary, it is delta G on sigma. Then what's this definition? It is G on the boundary of sigma. And then what's the boundary of sigma here? Okay, so if you compute it, it is 2 lambda minus the constant 1. Okay, so because this is the 3 side you have. Okay, 3 side. So lambda minus constant plus lambda. So 2 lambda minus constant. And then what do you get? So it is linear, so you bring the things up. But what did you see? This is 2 times g lambda, right? Because our ring is z mod 2z. So this term here goes to 0. So what you left is you left with g constant 1. Okay, I remove the minus sign because also of z mod 2. Okay, minus 1 equals to 1. Okay. And then we use again the identity that g constant 1 is equal to boundary of constant 2. Okay, which implies that I can push it to cohomology, become the core boundary map. But then, what is this? This is f cap f on constant 2. Have we computed this? This is we computed 0. So we get a contradiction of 1 equals 0. Okay. 金生讲写到第3年呢，还是一等于零。It's a very important contradiction. Okay. Right. Any questions so far? So it's not a core boundary, but it's a core cycle. So this is a non-zero map. Okay, so there are 2 ways I show you that the generator of the first level, the first cohomology is, what do I say? The cup product of the generator of the first homology is a generator of the second cohomology. 对吗？ 第一层的 generator 拿来 cup product 一下，是第二层的 generator。Okay. I have another example on genus 2 surface where you split it into octagon. Okay, you can have a look. Very interesting. Not too hard, the computation. And then also have 2 cell attaching to cell 1 with a degree m map. So you loop m times. Okay, maybe let you see the result. Let you see, have an idea of what is going on. What kind of answer you can expect. Yeah, you can go through the calculation yourself. I think it's a very fun exercise to do, so you can try and have a read. Okay, so this is the what do I, okay, this is a genus 2 surface. Okay, if you still remember the Hatcher example on cell complex. Okay, cell complex. Can you see the dotted line I draw there? Okay, you know what the dotted line means here? So this is one way to write down a map from simplex to ring. Okay, a Hom space. So whenever it intersects an arc, we will say that they take value 1 there. Okay, for example, alpha 2, right? It doesn't intersect B1, so meaning alpha 2 on B1 is 0. Alpha 2 on A2 is 1, like that. Okay, so we use the intersection to talk about the Hom space from the simplex to a ring. Yeah. I think this has something to do with the intersection. But this is a different space. So you can think of the dotted line as living in the dual space. Okay, the dual space of simplex. You evaluate the simplex. So in this case here, you get this result. You get this cup product property. Okay, this cup product property is very important. Can you see it? It is not commutative. Okay, it's not commutative. How to prove this is you check them on the same element, same simplex. One is the negative of the other map. 不一定是 commutative 的，还是 mostly 都不是。不一定。Yeah, 不一定。I mean depend. I mean I think if more than 不对，不一定。Yeah, 不一定。 Okay, so it's not commutative. So cut product might not be commutative, might not, 不是 always, might not. Although the coefficient ring is commutative, but cut products can be still not commutative. And then if you attach two cell to S1 by degree M map, so you map like M times, then you will get this homology where you will have a Zm term appearing in the level 2. Level 2 corresponds to the two cells, I guess. I mean, level 0 is obvious because it's a path connected space. Okay, but otherwise, it's 0. So M equal to 4K, you can cut the space like this. Anything I want to show you here? Maybe something interesting on this cut product here. What's beta? What's alpha? Okay, so if you look at this, right? This is non-zero. Why H1 got stuff? So interesting that H1 都没有东西，什么？我是少写东西，不是吧？Oh, okay. So this is the Z coefficient. Okay, this is Z coefficient. But if you move to Zm coefficient, right, there will be non-zero term in 0, 1, 2. Like the RP2 case, makes sense or not? Because you multiply by M, right? So then the boundary map becomes what? Multiply by M. Okay, because RP2 is like you gluing Z to Z2. So you gluing the boundary twice. So this one boundary map the boundary M times. So it is equivalent to the multiplication by M. Okay, so if you move to Zm, then it will become a zero map there. Such that you have a non-zero term in three levels. Or because if you look at this, cohomology ring, right, this is not interesting. Why is it not interesting? You only have things in 0, you only have things in 2. So if you take two elements in 2 multiplied together, you get to the fourth cohomology level, right? But there's nothing there. Okay, so it's not interesting for this one, but it is interesting here. There's non-trivial cut product here. Why? Because if you take two cut generator in level 1, it will move to level 2. Okay, and then this is what we computed. If you follow this calculation, it will be equal to K times some generator in the level 2. Okay, very weird, huh? Very, very weird. Okay, yeah. So far, any question? No? Any questions so far? Okay, so how to verify this equality is just a map checking. So you need to check on simplexes. Where you need to check on simplexes. Okay, then you can define what's relative cut. So relative cut here very interesting. One of them is relative. You will end up in a relative cohomology. Okay, as long as one of them is relative. Okay, as long as one of them is relative, then you will end up in the relative cohomology. So there are 3 ways to land inside here. Module. You can think of module, but this is not what I wanted to say here. Yeah, this is just saying that if you take the absolute homology with a relative homology, cut them together, you will live inside a relative homology. Okay, 3 ways to stay inside here. Okay, as long as one of them is relative. And in particular, if A is a point, we get the cut product on a reduced cohomology. Okay, so you can define reduced cohomology through this relative cut product because you just take A to be a point. So in general, right, you actually can take cut product between 2 different relative cohomology. And then you end up with the relative cohomology on the union. On the union, not in the intersection. Okay, union is more lenient. Okay, union is more lenient here. Okay, another thing is a cup product is factorial, meaning what? If you apply induced map on the cup is equivalent to you induce two of them and then cup them together. Okay. Yeah, this proof is very straightforward, so let's skip it. And then this is what we call the natural transformation. Okay, so cup product is a natural transformation. And moreover, it is a graded ring of morphism. So you will preserve the alternating manifold. So the natural question is whether the cup product is commutative. So this is answered by the following here. So just now we said that it's not always right. So what exactly happened? What exactly happened is you need to depend on what kind of cup product, which degree you take it out. Okay. So it is -1 to the k times L. So k is the degree of alpha, beta, L is the degree of beta. And just now in our case, what happens now? In our case, y got minus sign up. In our case, y got a minus sign. What did we do just now? See. Okay, so this alpha 1 and beta 1, where I pick them, let's check. Where I get this alpha 1, beta 1. So H1 only. See. Oh, okay. So actually, alpha 1, beta 1 are the cohomology class correspond to these simplex. Okay, it's the dual element to this simplex here. And then when they cup them, yeah, it's -1. Why? Okay, if you look at this formula here, what happens here? They are both coming from degree 1, right? So -1 to the 1 times 1 is what? -1. Okay. Yeah. So there's a minus sign. Okay, this proof is very super long plus combinatorics. So no need to see also, okay. Okay, lastly. So last before we end. Then we will form what we call the cohomology ring with whatever we had just now, direct sum of cohomology group and then cup product. And then one question we want to ask is, if I give you any polynomial ring or graded commutative algebra here, can it be a cup product algebra of some space? Okay, in algebraic geometry, what we ask, I give you a ring. Is it a coordinate ring of some algebraic varieties or not? Okay, so in this case here, this is also a very hard problem. And for Q algebra, rational algebra, Quillen proved it. This guy is a legend as well. This thing is a legend. Okay, you can have a look. And there's some result on periodic sum. A little, unfortunately, very little known for the integer. You might think that integer is very easy. Maybe I can throw one question to you. Any relation between coordinate ring and this product algebra? For those who take algebraic geometry before, any relation between them? Okay. Yeah. Any relation between them? Are they directly equal or something like that? Yeah. I mean, it's a natural thing to see, right? To ask, right? Question, right? Or could I obtain coordinate ring from cup product algebra, or can I obtain cup product algebra from coordinate ring? Okay. Yeah, because it's another way to attach a ring to your function, right? So in algebra, okay, maybe for those who haven't taken algebraic geometry before, what's coordinate ring? Coordinate ring basically is just a function that define on that space. Very similar here. This is called homology. but cohomology defined from your chain complex, not entirely on your space. And it is topology, okay? Right. So I asked Gemini. So it is true in some case. I mean, true meaning you need to take some quotient. At least it's true in the Lie theory or the geometric invariant theory. Okay, in those spaces. So that's why yeah, that's why those stuff is very interesting to study. Okay. Yeah, so there's some intersection theory going on there as well. Okay, 350. Shall we stop here? Can we stop here? Or module? Let's see what else we can do. I think we can stop here. For the point correct duality, right, I'm not planning to go into all the details. I just want to tell you there's some facts on point correct duality. And then how do you see who start from this point correct duality? We won't go into technical detail. But cup product, definitely we will test it. Okay, in particular, test on you how to check two spaces is homotopy equivalent. Cup product. This is the only question we will ask cup product. Use cup product to determine whether these two spaces are homotopy equivalent. Okay, later we'll see example on how to use them. Okay, point correct duality, we will just mention it and then maybe let you see some cool application. That's it. Any question? 啥是 graded ring？ 我可以进去一下子，到了其实。Okay, so it's just direct sum of additive subgroup. So meaning all these level of AK you can add in within them, but the multiplication will go from AK times AL to AK. Obviously, you can multiply within AK, but not within AK. After you multiply them together, it will jump up to A2K. This is the definition of gradient ring. Okay. And then the elements of this AK are elements of degree K. Or sometimes we call it dimension in this class because dimension is more relevant here. But in general, it's just degree because there's no cell dimension of cell appearing there. So we just call it degree. But in this class, usually we deal with algebra or ring that's associated to topological space, to CW complex, to delta complex. So that's the generator is dimension of some cell. So that's why we use dimension. In general, ring theory, we just use degree. Okay, so we start at graded ring. Let's continue. Yeah.
见而